Hey everybody, and welcome to Linear Algebra. I wanted to start today and show you something we would have done if we were together. If you pause the video and look at these instructions, this is actually out of the book, and I really actually like this game because it kind of sums up one of the most important things from linear algebra, and that's what's written right here in blue, linear combinations. And this is probably like one of the more important concepts in this course, and it's not too complicated to think about. I mean, basically it's saying, if you paused the video and looked at those rules, basically what we were going to do is we were going to kind of go through a racetrack thing, and we were going to use different vectors, but we were going to still end at the same spot that we started at. And in linear algebra, there's lots of times where we might add up a bunch of different vectors together, but we could have done that with one vector here in blue. In more mathy terms, this idea is basically given right here. So a lot of you might have not seen this before. This is just saying that, and this is really true for a lot of our courses here. So the vectors that we have down here, they don't necessarily have to be real valued. So this is basically saying that this definition just works over the complex field. And the M is really just there to say, it could work in any dimension. So we could do this in R1, or not R, but C1, C2, C3, whatever. And a linear combination is just these alphas, right, are all different scalars. And so we're saying U1 might be this vector right here. And we're going to scale it by something to get it to this size. And then we're going to add to that some other scaled version of a new vector. All right, and then we're going to add to that some other scaled vector, and so on and so on and so on and so on, however many times you want, right? And these red vectors are just basically here, right? And all of this should add up to becoming some new resultant vector. That's all linear combination is. And you might want to ask, why would I care about this? It's not that hard to understand this definition. The reason we care is really something we're going to kind of keep coming back to all year, but I can start with kind of a simple problem to motivate this. So if you take this question, and anytime I post these questions in a video too, I recommend you pause the video and try and answer these questions on your own. If we were together in class, I would have basically asked these kind of questions to you. And there is a really important tool that all of you have seen, but you might be a little rusty on it depending. I know some of you used this last year with me, but not all of you. But if you were asked, is this vector a linear combination of these three? There's always guess and check, and you could just try and see if you can scale this, and scale this, and scale this, and add them together in some way to get that. But really, the absolute best tool, which you will probably be very, very sick of by the end of the year, is something called reduced row echelon form. And so if you just make a matrix of 5, negative 4, 0, 2, negative 3, 1, 1, 0, negative 1, and augment it with 2, negative 2, negative 1, and then if you ref this thing, it will give you, I just did this on my calculator 2 seconds ago, it will give you 1, 0, 0, negative 1, 0, 1, 0, 2, 0, 0, 1, 3. And what this means is basically I can take negative 1 of the first vector, because that's in the first row, I can take 2 of the second, I can take 3 of the third, and if you add that stuff together, I promise you, if you do 2 times 5, negative 4, 0, and then plus equal 2, negative 2, negative 1. If you do, 2 of the second and 3 of the third, those will add to give you that vector. The fact that there's actually only one way to do this is another really important linear algebra concept. So we will talk about this a lot more, but the fact that you're not getting an infinite amount of ways to do this, that there's only like a single solution to this matrix, implies that these vectors here are linearly independent from each other. If they weren't linearly independent, and like one was a scalar of the other, then there'd be a whole bunch of different ways to get this combination. So this sums up a lot of kind of the techniques that we'll do this year in this problem, actually, but the conceptual part of this is kind of what's almost more important. So say you have these two vectors, v and u, so 2, 1, I think I drew them out right, 1, 4, yeah. So if so these like the v can move anywhere, right? So I could put it right here, and extend it down here too. I'll do another one too. So we'll do right there and then there. This vector right here is the same every time, right? You can move around in space. As long as it has the same length and direction, it's the same vector. And this is not the same vector, right? Because it's flipped. But and assume that's a straight line, basically. If I do that same kind of thing for u, okay, so if I go here and extend it, if I go here and extend it, what we do a lot of times, linear algebra has applications just all over the place. And one of the things that linear combinations is really useful for is that a lot of the world is just not easily described by this x and y axis or x, y, z or whatever dimension you're in. It's too, in a sense, rigid to assume that you have a nice orthogonal basis. Well, that's a fancy word. I shouldn't use that word yet. It is too rigid to assume that you have perpendicular lines that could describe the space. We'll call it that. And so one other kind of concept is we may want to describe new vectors in terms of things like u and v. And these can actually, in a sense, become sort of my I and j, or like my new kind of simplest vectors. The word I'm trying not to use is basis. We'll talk about that soon. But like a linear combination of these two vectors would be really any vector that ends at an intersection of these kind of new grid lines. So, if I draw this one in, okay, if I go, I guess that would be about half of v, and then I go, I think that's negative u, right? So if I go half of v, negative u, I would get this green vector that I drew right here. And that vector is a linear combination of the red and the blue ones. And so, I'm thinking of things like if you go into material science and you're working with like a crystalline structure, you might not be able to describe it in terms of like the x and y vectors, basically. And you might have like a more interesting kind of, weird geometric shape. And linear algebra can let you describe that crystalline structure with basically new vectors. So this could be, could be part of that crystalline structure, and you could describe it with these two vectors, u and v, instead of having to describe it in terms of x and y. But you could do this anywhere. It doesn't have to be this. You could do this vector, anything at all that ends right here is going to be able to be described with a linear combination of the red and the blue. And that's just a little taste of some stuff that we're going to do this year. There's a lot more to talk about here, but this is probably one of the more important definitions actually in the course, and you'll see it pop up time and time again. All it is just saying add up a bunch of different vectors scaled different amounts, and we can do things like this, where we can figure out if we have a linear combination by using reduced row echelon form. We could create new vectors out of linear combinations of other ones, and that is about it.